Hold on. There it goes. Okay. There we go. All right. So I think it's fair to say we are now like up to date, if you were, on grades other than 3.1. But I think at this point it's fair to say you all now have a really accurate picture of grades in the class. How did homework 3.2 go? And by the way, there was a question before class in terms of the disparity between the bolt shear capacity and the bolt bearing capacity on that homework, that if you did it right, you should have got a bolt bearing capacity that was way higher than the bolt shear capacity. Did anybody else get that? I mean, we're talking like, I don't know, like 280 kips versus like 900 or something. It was different, okay? And it's just because, I mean, there's a lot of bolts in that connection. There just are, okay? There just are. Any questions? All right, just a heads up on logistics. So we don't have a test coming up like anytime soon, but we do have a test coming up between now and spring break, okay? It'll be the week prior to spring break, and then what we're gonna do, so we're gonna have a test the week prior to spring break, and then, or sorry, not the week prior to spring break, the week before that. And then the week prior to spring break, we're gonna have class Monday, we're gonna have class Wednesday, we're not gonna have class on Friday. Is that okay? I figured you wouldn't mind that. Okay, with that, let's finally start talking about some bolted connection design, okay? So over the past couple of lectures, what we've talked about is bolted connection analysis. So we're doing this sort of the same way that we did tension members. Remember, with tension members, we had a series of lectures just focused on assessing a tension member. Here is a member, what is its capacity? Here is a member, does it satisfy design limits? And then we said, okay, here are some loads, design a member for those loads. Well, now we need to start talking about this from a connection standpoint. Recall that we have both bolt shear and bolt bearing as our limit states to assess. And by the way, I finally remembered, I have a bolt. Okay, this is a A325, I think this is 3/4 inch diameter A325 bolt. I wanted to pass this around. I wiped it down a little bit so it shouldn't be too dirty to the touch, but I guess you might get a little bit on your fingers and whatnot, but I'm going to pass that around. And you can kind of see the difference between the threads being included and the threads being excluded from the shear plane, okay? Now here's the bolt shear capacity table. Here's the bolt bearing capacity equations. I think by now we should be pretty comfortable with those, be pretty familiar. Everybody good? Okay. And here's our layout requirements. Now, our layout requirements are going to be pretty necessary for the purposes of laying out connections, because we're going to be given members and the idea is to design a connection. Okay, so we are going to need to use those as a reference. One thing I'll tell you is that I will make sure that you're aware as to whether or not we're going to be using minimum bolt spacing or preferred bolt spacing. Okay, I will make sure that you're aware of that. Let me log out of this. Okay. All right, so let's talk about design. Design, I think that you all could probably conceive of a design procedure in your heads without too much difficulty. I mean, I'm going to keep it real simple. If I have a connection that needs to support 200 kips and each bolt can support 20 kips in shear, how many bolts do you need? Just take the load divided by the capacity per bolt to get the number of bolts. That's it, right? That's pretty much all there is to it. So what we do is we get our factored load, we determine, so the way that we design a bolt, the way that we design a bearing type connection is we determine the shear capacity of a single bolt, and then we divide to get the number of bolts. And I have a couple notes here on selective pattern accordingly and whatnot. I'll talk about that here in a second. But in terms of placing those bolts on the connection, you'll either use, either S min or S preferred, and typically you'll use the minimum edge distance. And some of you might ask, well, why would we use minimum edge distances? Why would we use minimum spacings? Why wouldn't we use maximum spacings? Well, the reason why is pretty straightforward. If you have, let's just draw it out right here. Let's say I have a column and I have a column, okay? And I have two tension members, and it doesn't really matter whether they're tension members, it doesn't really matter. Let's just say I've got two members between these two columns, okay? Now, the member up top, I'm going to use minimum spacings and minimum edge distances. So I'm going to pack those bolts together as closely as possible. So that means that the plate that connects them is going to go like that, right? Now the one down below, I'm going to use maximum spacings. Maximum, sorry. I'm going to use maximum distances. So the plate that connects them is going to be that much larger, right? Sorry, my pen's wanting to go down to this thing. So the point I'm making is that which connection plate is more expensive, mine or yours? Yours, right? So having a connection with maximum bolt spacing, maximum edge distances is just going to result in a connection that's more expensive. Does that make sense? So we typically try and go with minimum spacings, minimum edge distances to create a more economical connection overall. Okay, now that doesn't mean that we can space them so close that they fail bolt bearing, which is why we have to check bolt bearing at the end. So I just want to throw that out there for discussion purposes. Now, I want to give you some additional items to consider before we do an example. So the first thing I want to talk about is step 5, okay? So if we go back a slide, what happens is, we determine our factored load, we determine the shear capacity of a single bolt, and then we divide to get the number of bolts, and we lay them out. And then the last thing that we do is we check our bolt bearing capacity. And if bolt bearing capacity fails, we iterate. What does iteration mean? Like what happens there? So it's possible that you check step 5 and you find that bolt bearing governs, that you find that the connection does not have enough capacity. There are a couple of ways to go about this. One of the things that you could do is you could increase your bolt spacing or increase your edge distance. Like as an example, if you barely fail bolt bearing, remember bolt bearing is a function of the spacing between bolts. So if you upped your bolt spacing by like a ½ inch or a ¼ inch, that might be enough just to solve the problem, okay? So that is usually a pretty straightforward way to go. You could also stagger the connection. We're not going to do that, but remember in tension members you could have a staggered connection. You could stagger your bolt arrangement, and that would slightly increase the bolt bearing capacity because you would have a couple bolts that would have a higher edge distance capacity. So that could work. The other thing that you could do is increase the number of bolts. Instead of 12 bolts, maybe use 15 bolts or use 14 bolts or whatever. And I would say, like personally, I would only do that if you really needed a lot more capacity. Like if the only way to overcome the discrepancy between applied load and resistance, if that chasm is so great that the only way you're going to cross that is to add bolts, then okay, maybe consider that. But if it's only a slight difference, I'd probably tweak my spacing a little bit to make it work. The other thing that I would do also is I would choose a bolt pattern that makes sense, okay? And what I mean by that is if you're laying out bolts in a grid, like a rectangular grid, and let's say you have the design load, the PU, and you have the shear capacity per bolt, and you divide to get the number of bolts, so let's say the number comes out to be something like 10.46. Do you round that up to 11, or do you round that up to 12? And I would probably round it up to 12 so that I would have a nice like 3x4 grid of bolts, okay? 11 bolts would be kind of odd to lay out, if that makes any sense. And it doesn't really make sense. There's also stagger and all this stuff. And if you're not intending to do that, just round it up to 12. It's really not going to be a big of a deal. So I would just say that, make sure you're choosing a pattern that makes sense. Many fabricators do prefer to lay out bolt connections or bolt patterns in a 3-inch grid. So that's what I mean by that is using a bolt spacing of 3 inches and an edge distance of 3 inches. Like I could tell you right now, if I was, so we've got some senior design teams I know that are working on some connections, and if you asked me just without any context, any loads, anything, and you asked me to just rough out a connection, I'd probably say, why don't you try out a 3-inch spacing just to get started, and we can tweak it later. Okay, it's sort of my go-to without any science to it. And the reason why is because a 3-inch spacing for both bolts, both bolt spacing and edge distance, meets the layout requirements for 3/4 inch bolts. It meets the layout requirements for 7/8 inch diameter bolts. It meets the layout requirements for 1-inch diameter bolts. So it's a nice pattern that meets spacing and edge distance requirements for a wide array of bolt diameters. And so it's kind of nice to use something simple, because if you've got a project where you've got hundreds and hundreds of bolted connections, and you're just trying to come up with something that makes sense, and you're trying to come up with a bolt pattern that makes sense from a fabrication standpoint, where you can create repetitive connections, regular increments to make the fabrication process a lot easier, then a 3-inch spacing might make sense. Yeah, you might have some connections that are a bit over designed, but think how fast you can get them through the fab shop. You know what I mean? So it's something to think about, that it's beyond just the raw numbers of what's listed in AISC 360. So far, so good? Okay. Now, there is another process I want to mention, and I want to mention the term designing to develop the full capacity. And that is, so this term, designing to develop the full capacity, that is somewhat unique, and this is the first time we've ever seen something like this. I don't know whether or not we'll have a problem like this or not on maybe an exam, but I did want to mention what this means. Okay, so here's what this means. If I give you a tension member and I say the tension member's got 200 kips on it, design a connection, you're going to take the 200 kips, divide it by the shear capacity per bolt to get the total number of bolts, right? Okay, well, what if I say to design to develop full capacity? What is the load? The load is the gross section yielding or net section fracture capacity of the member, okay? So what you'll do is you'll say, okay, let's say I have a channel that's got 2 lines of bolts through the web. I'll compute gross section yielding, I'll compute net section fracture, and I'll use that as a load and to use that divided by the shear capacity to get the total number of bolts. The logic behind doing that is that it doesn't really matter what force is on the member, the connection is going to be able to hold it, right? Because the connection is going to be stronger than the member, but just stronger than the member, just barely stronger than the member. Does that make sense? If you were to ask me to design a connection and you didn't give me any knowledge whatsoever about what loads the connection was going to see, like if you have a brace in a building but you don't tell me what the loads are, you don't tell me what bolt spacing you would like, I would probably just use 3-inch spacing and design to develop full capacity. The downside of designing to develop a full capacity is that the connection is a little bit over-designed, but the upside is it's not going to fail. So it's something worth mentioning. So like at a minimum, if I was working on a project, I might start by designing to develop the full capacity so that I can get a structure finished, and then go in and start tweaking connections later to start to economize it and shave down some weight. So sound good? Let's do a problem. Okay, so I've got a, let me get out of this. I got a lap connection here. It is a 12-inch by 7/8 inch plate. I'm using 3/4 inch diameter group 150 bolts. So we're not using 120s. I've got A572 grade 50 plate, and we're going to design a lap connection for the following loads. So 115 kips of dead load, 160 kips of live load. Okay, I'm going to show you the process of designing a connection, essentially start to finish, and let's see what we come up with. Okay, so, and we'll I'll go through a couple of side notes on this as we move forward. Okay. All right. Okay. So our first step, given this data, is going to be to factor the load. Okay? And what we'll do is we'll just use the loads that are given. And so what do we got for this? Say it again. 442? I got something different. I got 394. Is that what you got? Okay. And then what I'll put over here is a note. So if I was trying to design to develop the full capacity, maybe what I would do is I would say PU is the minimum of 0.9 FYAG or 0.75 FU. Remember AE, remember how the spec says AE, and then AE is the net area times U. And so maybe what we'll do is we'll do that, and we'll maybe we'll assume that. Because remember, that's what we used when we were in design land. So we would use that for our load, okay? So it's just something to think about. And I mean, like, it would result in an over-designed member probably, but not a grossly over-designed member, because you would think that the member itself is designed for these loads. So it shouldn't be that, over-designed itself. So, okay. Does that make sense? Everybody okay with that? Okay. All right. So, next thing we need to do, is we need to figure out the number of bolts in this connection. So, in order to determine the number of bolts, we need to determine PRN for a single bolt. Okay, and I want to be clear that this step right here is the only thing that changes between a bearing type connection and a slip critical connection. And we're going to talk about slip critical next time on Wednesday. So just to throw that out there, that's the only thing that changes. Okay, so determine PRN for a single bolt. So we're going to go to table 7.1. So somebody help me out. What data in table 7-1 are we going to need in order to be able to determine the capacity of a single bolt? So first off, what group are we dealing with? 150. Are they included or excluded? So we've got group 150X.
group. What's the bolt diameter?
3/4.
And one other thing, are we dealing with single shear or double shear? Single shear, there we go. Okay, and so based on these parameters, what is phi RN?
27.8.
Okay. I think I have a second. So 27.8 kips per bolt. Okay? So that's how many kips it will take to shear through this bolt. And again, we're assuming that based on the geometry of the connection, that the shear plane is through the shank of the bolt and not through the threads. Okay. Which, I mean, is not unreasonable given the thickness of the plate. I mean, if you had this bolt and the plate was relatively thin, you could shear through that and not the threads. So, okay. Here, I'll just set that over there. Okay. So now what we need to do is we need to determine the number of bolts. Okay. So we'll call it NB min or whatever. Doesn't really matter. And so all I'm going to do is I'm going to take the load and divide it by the shear capacity of a single bolt. So how many bolts are we getting? Let's actually calculate it out. Let's embrace the decimals, as it were. 14.17. So I guess my first question is, can we just use 14? No, that's not enough. Yeah, so we don't round down this number. We got to round it up. So would 15 make sense? I mean, can we get a nice little pattern on 15?
Yeah,
3 by 5, right? Or 5 by 3. So there we go. Let's use 15 bolts. Now, I heard somebody say, what about 16? I want to hold off on that discussion point right now because I think we'll have a more intelligent discussion about it here in a second. Okay? Like 16 might work, but 15 might work too. Okay? So it's all a geometry problem. Okay. So now we're going to use 15 bolts, but what does that mean? Well, we need to actually lay it out. We need to actually design the connection. So we need to lay out the connection. Okay, so let's lay it out. Now, my apologies for the scrolling. I know I'm doing a lot. Okay. Now, what we're going to do for this problem is we're going to use minimum bolt spacing. Okay. In other words, remember we have an S min and an S preferred. I'm going to use S min. Okay. So let's see what we can see. All right. So first off, we need a minimum edge distance and we need an S min. Now S min's pretty easy. How do we compute S min? Let's do S min first. 8/3 of the bolt diameter. And the 3's cancel. That's 8/4. That's 2 inches. Okay. Now, what's the edge distance? How do we get that? Anybody remember? I see pages of fluttering in the manual, so I see some of you remembering that we looked that up. In table J3.4.
1 inch. Everybody else find that? Okay. So we've got an edge distance of 1 inch and a bolt spacing requirement of 2 inches. Now, before we move on, I want to ask a question, and there's a reason I'm asking this. I know it seems redundant, but just bear with me. Why do we have bolt spacing and edge distance requirements? Like, why are they there? In general, I'm serious. I want a simple water. Okay, water and facilitating construction, right? Like if the bolts get too far or get too close together, we can't wrap a wrench around them. We can't. If they get too close to the edge of the plate, you start having fab issues and corrosion, right? So it has nothing to do with strength, okay? All right? But because it has nothing to do with strength, it has nothing to do with the bolt bearing capacity of the connection. We as engineers are free to arrange the connection right now in whatever way we would like, okay? So here's my point, okay? I propose we have 2 options. Okay. Now, if we have the number of 15 bolts, what grid pattern? If it was 5 by 3. So my question to you is, should we do 5 by 3 or should we do 3 by 5? Let's think about it. So one option would be this, and here let me kind of do that, kind of do that. That's an option, okay? All right, and by the way, how wide is the total plate? Like, what's the total width? Like, what is this distance? 12 inches. So what that means is that if we did this dimension here would probably be like 3 inches. Like we'd probably space them evenly, right? Same thing with this distance right here. And then what we would do is we would do 1 inch, 2 inches, 2 inches, 2 inches, 2 inches. Like real quick, does this pattern meet bolt spacing requirements? I mean, I think it does, right? Keep in mind, though, that the plate that's connecting on the other end, we'll draw that in red. I got to have a plate out here. We'll make it bigger. I have a plate out here that's got to go all the way down there, right? Does that make sense? Like, in order for a connection to work, I got to have a plate that goes through here, 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 and maybe like a 1 inch distance right there. With me so far? Now, here's another option. Let's do 1, 2, 3. Let's do that. Huh. All right, so let's lay this out. Okay. We'll do one, two, 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 one. Okay. Now, before we start figuring out dimensions this way, the reason I brought up the whole corrosion and wrenches and all that is the following, okay? Does the connection meet bolt spacing and edge distance requirements this way? I would say yes. But a follow-up question, does the connection have to meet bolt spacing and edge distance requirements this way? Does it have to? Well, do we still have a corrosion problem this way? Do we still have getting a wrench around the bolts problem this way? Yes. Okay? So you said 16 bolts. A 16 bolt pattern would be 4x4, right? So a 4x4 pattern might make sense if we fail spacing and edge distance limitations this way, right? We can't have we couldn't do this if the space between bolts was like ½ inch. That wouldn't make sense, right? We still have to meet edge distance requirements and spacing requirements all around because they have nothing to do with strength, right? So we can lay out the connection any way that we want, provided we meet these limits, okay? So I guess my question is, if we're evenly spacing it this way, what are these distances going to be? How many of them do we have? 1, 2, 3, 4, 5, 6. So what is that going to be? 2. Is that going to meet bolt spacing and edge distance requirements? Yeah, it will, right? Because S min is 2 inches and the distance between bolts is 2 inches. So now my question to you is, if you had an option, which one would you pick? Assuming that they both meet bolt bearing. The bottom one. Because the bottom one is going to result in a connection plate that's a lot shorter, right? Like what I'm saying is, what's cheaper? This lap connection or that lap connection? This one has less wasted material. You see what I mean? So go with this one. I propose this connection makes more sense. Okay? Now, I am also proposing that, assuming it meets bolt bearing. We have to figure that out. So let's actually formalize that a little bit. Okay? So here's my trial connection. This is my trial connection. Okay, by the way, how many edge bolts do I have on this connection? And how many interior bolts do I have? 10. 5 edge bolts, 10 interior bolts. That's different than this connection that would have had 3 edge bolts and 12 interior bolts. Does that make sense? Okay, now, again, this connection is not going to work if it fails bolt bearing, which is why what we need to do is evaluate bolt bearing. Now I'm going to do this real quick because I think at this point bolt bearing is something that we're all familiar with. Okay, so let me sort of do the diligence here. Okay, so here's what I mean by that. Okay, we have an S of 2 inches, an LE of 1 inch. We have a thickness, a plate thickness of 7/8, and that came from the problem definition, right? Because up here we have a plate of 7/8 of inch thick. Okay, So we've got a bolt diameter of 3/4 of an inch. So therefore, the hole diameter is what? Not 15, 13. Yeah, but you're on the right track that you're adding a 16th, not an 8th. And we also know that FU in this case is 65 KSI because it's A572 grade 50. Okay, so like I said, I'm going to do this part real fast, but you know, what do we have? We have LCE, LCE, which is LE minus 1/2 DH. We have LCI, which is S minus DH. I'm going to go ahead and just do these for you. This comes out to be 0.594 inches. This comes out to be 1.188 inches. And so that's sort of our first step. Then the second step is 1.2 LCE TFU, 1.2 LCI TFU, and 2.4 DTFU. So that's sort of our second step. And like I said, I'm going to go ahead and do these for you. This comes out to be 40.52. This comes out to be 81.05. Am I okay to do this pretty fast? Is that okay? Because we've done this a few times. So 102.38. Okay. And then what do we do from here? All right. So we take the minimum of these two for edge bolts, the minimum of these two for interior bolts. So therefore, oh. And then we take RN as how many edge bolts we said? We said 5 edge bolts plus 10 interior bolts. And that comes out to be like 1013.09. And then phi RN is 759.8. So is this connection fine in bolt bearing? Well, remind me, what was the load that we were designing for? So is it fine in bolt bearing? Oh yeah, it's fine. So I would say step 6, no iteration necessary. Bless you. Bless you. And so what I'm essentially getting at is, what's the answer to the problem? That's the answer, right? We laid out a connection. We evaluated its bolt bearing capacity. We found out its bolt bearing capacity is way higher than the load. So we're good. And that's our answer. Okay? Does that make sense? Does it make sense why we arrange the bolts one way versus another? Does that part make sense? Because we want the connection to be as tight as possible so we don't have to waste material with plates. I mean, every connection has plates that go along with it. I mean, like it might sound silly, but I mean that stuff. Well, I don't know if it sounds silly. I mean that stuff adds up. I mean, like if we go back to, and I know we're running out of time, but I'll be quick. If we go back to, I don't know, like these connections here, I mean, the more material, the more this connection gets spaced out, the more plate behind that web has to exist, right? That's more money that may not be necessary, okay? So we want the connection to be as compact as possible so that we can save our clients some cash, but it's also obviously got to be safe. Sound good? Yes.
Do you not need to worry about taking away from the net area where you have the line?
That's a great question. That's a fantastic question. That's probably one of the best questions I've ever got on this. The answer is yes, because you are doing the net area minus so many bolt holes, right? Another reason why designing to develop the full capacity, if you assume on the onset that you're reducing by 5 volts, then there you go. So this is another potential where you might have to iterate in the future. Like you might look at this all said and done, and then you find that your plate doesn't have as much net section fracture capacity or block shear rupture capacity or anything like that, in which case you might need to iterate further. You're not wrong. You're actually right. So you stole something I was going to talk about on Wednesday. So, all right. We're running it short on time, so that's all I got, everybody. I'm going to pull up the code one more time, but I'll see you all on Wednesday.